record this so that everybody has the benefit of doing it. I want to take just a minute to go over a couple of the homework questions to make sure that your answers are happening in the right format. Did you all find that last night's problems were pretty easy? Yes?
Yeah.
No? Okay, good. So when problems are really easy, the introductory problems, that's the time to work on your format. It's kind of like when you're firing a gun. When you learn to fire a gun, you don't just pull it out from your pocket and shoot. You take a stance, and then you fire. And the same thing happens here with our problems. These are easy problems. So we're not going to stress too much about how you get the answer. Instead, we're going to not stress about, but we're going to practice doing it right. So you want to check and make sure that your answers have all of the following things. First of all, with number 1, you want to make sure that you have a free body diagram. If your work does not have that free body diagram, then you're doing it wrong. Yeah. So, make sure that you have the free body diagram. If you don't have the free body diagram, write yourself a nasty note that says free body diagram every single time. So I did say that yesterday a couple of times, and I meant it. Now that you have the free body diagram, then you're going to go straight to Newton's laws. Is this a Newton's first law or Newton's second law problem?
Second.
Definitely second, that's right. And so you can say that the sum of forces is equal to mass times acceleration. If you said F net here instead of sum of forces, then that's a perfectly acceptable synonym. So either one of those works. And having said that, we now have only one force. Here's why we do the free body diagrams. Once you got the free body diagram, your sum of forces comes directly from the diagram. There is no guessing. You look at the diagram and you say, hey, what forces do I have? Oh, the force is F, because my diagram says so. And then, having done that, you set that equal to the mass, whatever it may be, times the acceleration, whatever it may be, and make sure that the units are in there. Sometimes problems will be tricky and they'll give you masses in grams, and if you don't put the units in there, you'll get fooled. And if you do, then you won't. And then you can either write it with the product of the units as stated, or since we all know that a kilogram meter per second squared is a Newton, you can write it with a synonym. So all of this needs to be what your work looks like. And it's easy peasy, right? So some people will just try to skip straight there because they can see all that in their heads. But the problems will get harder. And when you have this format down, then they don't get much harder. Does that make sense? Okay. Armed with all of that, I was going to do a Quizlet today, and then I realized that half of you aren't there. So we'll do a practice Quizlet. Here it is. You can just do it right in your notes. Give me Newton's 3 laws. Go. I kind of knew I was going to ask that, didn't I?
You just need to do it in mathematical terms.
Yeah, mathematical form is best. Monica, law number 1.
N equals 0.
Under what condition? Yeah. I want you to notice, math has meaning, right? And the meaning of what you just said is that the acceleration of everything is always 0. So that's probably not true. The question is the acceleration of what objects? Yeah.
If f net equals 0.
Yeah, here we go. And that actually goes both ways. It's if and only if. Hi. Come on in, sit as far forward as you can. So what if f net is not 0? Demani. Second one.
F net equals
That's it. If the sum of forces or the net force is not 0, then that net force is equal to mass times acceleration. And then finally, Newton's third law.
FAB is equal to negative F net, or BA.
Yeah, exactly. For every action, there is equal but opposite reaction. And the FAB and the FBA are always on different objects in your free body diagram. This is on object B, this one is on object A. For the benefit of those watching at home, that one is on object B, and that one is on object A. Okay, we're going to talk about the difference between weight and mass today. And so to do this, we actually have all the tools that we need for it. I'd like for you to draw the free body diagram for an object that is in free fall. Do you remember what free fall means? Free fall is a very specific meaning. Grant, what does that mean?
That there's no, that it's not going to it's falling straight down.
Nope. No.
Falling
Sure.
without errors, resistance.
Nope. What does free fall mean? It has a very specific meaning. Yeah,
The only force on it is the gravity.
that's it. The only force on it is gravity. If there were an air resistance acting on it, it would not be in free fall. This is a very literal definition. So that makes the free body diagram kind of easy, doesn't it? Now, I'm supposed to draw an object that is in free fall. Do I know the mass of this object? No, so how do I handle that? Since I don't know the mass. I may end up solving for the mass, but since I don't know what the mass is, what's the basic thing that we do since Algebra 1?
Substitute or solve the
Not the units, but put a label, right. That's the spirit of algebra. If you don't know something, call it a variable. So I'm going to do that. And my favorite variable for mass is m. Now what force shows up on my free body diagram? And how do I label it? Many forces. You didn't remember it was in free fall.
gravity, so you draw an arrow underneath the box pointing down.
And how does it get
Let
labeled?
FG.
Yeah. FG. That's it. Okay, so here is an object in free fall. Every single object in free fall looks exactly like this. We're going to give a name to this. The force of gravity acting on this object is called the weight of that object. The weight is the force of gravity. Now, there is a problem, and that is that in common language, you know how in English sometimes two words that are similar sounding or relate to a similar concept kind of get thrown together and people start to use them interchangeably? So, for example, the word imply, which means to state something that then logically leads to something else is similar in concept and sound to the word infer, which is to reason from what somebody has said to come to a conclusion. So if I talk to you and I say, nice jacket, then I might be implying I want one too. You might infer that I'm saying that I want one too. So the difference is between the speaker and the listener. The speaker implies, the listener infers. Well, in English, very often, people will take and just mix those two words up. So they'll use imply for everything. Well, the same thing happens with weight and mass. Weight and mass are actually really different. How do I know? Look, here's the mass, right there. And the mass measures the inertia of that object. And it's measured in kilograms. But the weight is a force. And it's measured in newtons. And these two are very obviously different on this free-body diagram because there's my weight, which is the force pulling straight down, and here's my mass just like that. I want to explore the difference between mass and weight just a little bit further by comparing and contrasting them here. I think I need 3 columns, rows. Let's do it like that. Okay? So if I have the mass, then the mass measures inertia, and it is a scalar quantity. You don't have 5 kilograms east. You just have 5 kilograms. Whereas the weight measures the force of gravity, and it is a vector quantity. Which way does the weight always point? Straight down, exactly. Because the mass is the inertia, therefore, anywhere you go in the universe, your mass will be exactly the same. If I go to the moon, if I go to Jupiter, if I go to wherever, my mass will be constant in reference frames that are at rest with respect to each other. If you're going really, really fast, like 9/10 the speed of light, then your measured mass will begin to increase noticeably. But for objects at slow speed, that relativistic effect is not there. So we're going to say basically mass is constant. And by contrast, the weight depends upon which planet you're on. So I weigh, yesterday I used 80, but I think it's closer to 700 newtons. I weigh about 700 newtons. And I have a mass of about 70 kilograms. If you take me to the moon, I still have a mass of about 70 kilograms, but my weight drops dramatically to be only about 150 newtons, something like that. So instant weight loss, go to the moon. This is one weird trick. If I go to Jupiter, on the other hand, then my weight would more than double to about let's call it, well, it's going to be a factor of 2.6. So it would more than double to somewhere around 1,700 units, something like that. So how much you weigh depends upon the planet you're on, but my mass will be the same throughout, and that's going to be really important for us. And the third thing has to do with the units. Our units for mass are going to be kilograms in the metric, and for the English, it's going to be a unit that you've never heard of and I never use, called the slug. And one slug is equal to, I had to look this up because I really never used this. One slug is 14.5 kilograms. So my mass is about 5 slugs. I can see the point of the name. If I were to throw a slug at you and hit you, definitely slug you. By contrast, over here, the weight is measured in newtons for the metric system, and for the English system, it's measured in pounds. So probably all of you know your weight in pounds. No? Do you know your mass in kilograms? What is your mass in kilograms? 63, 64 kilograms. So your weight would be 126 plus 12 plus 13. Going to be 139 pounds. 139. Yeah, that's about right. Okay. So, now, remember how I talked before about words that tend to get confused with each other? It's so bad, the confusion between weight and mass, that in common parlance, you will often see this. 1 kilogram equals 2.2 pounds. What does that even mean? How can I take a mass and compare that to a weight? Is that a true statement? Under what circumstances? I mean, this is a conversion factor that actually I use a lot. So, in what sense is this true? Yes, we are so used to living on the earth that it is a true statement that the weight of 1 kilogram is 2.2 pounds. And so we use that as a conversion factor. It's not a literally true statement, but you remember how conversion factors work, right? You have two things that are equivalent under some circumstance. This is only true on Earth. If you go to Jupiter, the correct statement would be that 1 kilogram equals about 6 pounds. And if you go to the Moon, the correct statement would be that 1 kilogram is about 0.35 pounds. Here's a better statement, but I haven't convinced anybody to start doing it yet. And that is that 10 newtons, really it's 9.8 newtons, equals 2.2 pounds. That's true everywhere, because now I'm comparing apples to apples, force to force. Well, okay. So, does everybody understand the distinction here between mass and weight? Put it simply, mass goes in your object on the free body diagram. Weight is a force that shows up as a force in the free body diagram. That's the takeaway. Now, back to our free fall object. We've drawn our free body diagram. Let me replicate that on the next page. And what we'd like to do is to explore that weight just a little bit more. Here's what I'd like for you to do. First question. What is the acceleration of my object in free fall?
10 meters per second squared.
What symbol do we get to that? What symbol do we have for the acceleration due to gravity? G. That's right. So we can say about our object in free fall that the acceleration is equal to really negative G because it's going straight down. But if we just do the magnitude, then the acceleration, the magnitude of the acceleration is equal to G. All right, so we knew all those pieces. Now I want you to put them together really simply. Apply Newton's second law to this object. Go. And you should have that your net force, which is equal to the force of gravity only, is equal to ma, and the A is G. And so, what do we learn? We learn that the force of gravity is always equal to mass times G. That's it. We just learned how to compute the weight of an object. It's mass times G. So this is the definition of weight. Now, very quickly, because we've got like 5 minutes or less. Let's actually use this to solve a couple of problems. I've got a 20 kilogram mass here. Find the tension in the stream, like so. Okay. So where am I going to begin in solving my problems?
First, we need the free body diagram.
Bingo. What forces show up on that free body diagram?
The gravity.
Gravitational force is going to go straight down. And because I know that the force of gravity is equal to mg, and I know that g is basically 10, then I can label my force of gravity here as 200 newtons going straight down.
And then we know that if one force is working the object, there is another direction force going up, which is the tension that's translating to the other side.
Okay,
So,
I like your conclusion, but it's for a slightly different reason here. This is not the action-reaction pair, which always shows up on different objects. The reaction for this guy actually shows up on the ceiling. So the ceiling is going to experience a force of tension pulling straight down like that. So there's your Newton's third law happening right there. This is just two forces that happen to be acting. Okay? Now that, yes ma'am?
What is the 200?
The 200 is the force of gravity. I should have labeled it so you can see it on that object. Its mass 20 times the value of g, which is 10. If you wanted to be more specific about it, you could do it as 20 times 9.8, and in that case you would have it labeled as 1/9, the value is 198. 196. So either one works. I'll take either g is 10 or g equals 9.8. So now that I have this, the next question is Newton's first law or Newton's second law? And for that, we watch the object to see what it does. And as we watch the object, what does it do? It just sits there, right? And because it just sits there, therefore I'm going to use Newton's first law. Because the acceleration is 0, I can say that the sum of forces on the object is equal to 0 because it's not accelerating. And now I come back to my diagram right here, and I'm going to read the forces directly off of that diagram to put it into the sum of forces. And I have to remember that forces are vectors. They have direction to them. So, which direction am I going to take to be positive? There's no wrong answer. Just give me one. Yeah, okay, that's fine. So I'm going to use down as positive, and I'll put that right there. And that means that the force of gravity here is to be taken as positive, and the force of tension is in the opposite direction, which is therefore negative. And all that adds up to 0. Is everybody with me? So the key thought was, once I've got the free body diagram, that controls the sum of forces right there. And I don't have to sit there and puzzle about the sum of forces. I just look at the diagram and say, there it is. Well, solving, we've got it. The tension in the strain is 200 newtons. And that's it. Yes?
For problems like that, we have to show
Yes, and the work to be shown.
like the 200 minus the FTs and things like that.
Okay, yeah, so let me show you. Free body diagram, statement of the law, plugged-in statement of the law. This is formula, plug-in, and install. Yes.
This would be a plus, right? Because otherwise, it's out of direction. It's negative, to cancel out the negative.
If we did the opposite direction here, if we said up is plus, then FT would be positive, and 200 would be negative, and you would still get FT is equal to 200 units.
Yes. But why was it not negative 200 on this side?
On here?
No, on
Here. Oh, because I subtracted 200 from both sides and divided both sides by -1.
Oh,
Yeah.
thank you.
See you later.